About to talk about an object so dense, so unimaginably compact, that it defies everything we know about matter here on Earth. Picture holding an ordinary teaspoon. Now, imagine filling that teaspoon not with sugar or flour, but with the stuff of a neutron star. That tiny spoonful would weigh 1 billion tons. Yeah, you heard that right. 1 billion tons. That's heavier than the entire human population combined. Heavier than the Great Pyramid of Giza multiplied thousands of times over. It's a number so vast it feels meaningless, yet it's the cold, hard reality of physics pushed to its absolute extreme. It's not magic. It's the aftermath of a star's catastrophic death, where the fundamental rules of what stuff is get rewritten in the most violent way possible. To even begin to grasp this insanity, we need to understand what a neutron star is and where it comes from. It's the cosmic tombstone of a massive star. Not just any star. We're talking about giants, stars born with at least 8 times the mass of our own sunday. These stars live fast and furious lives, burning through their nuclear fuel in millions, not billions, of years. For most of their life, there's a constant battle going on inside them, the crushing force of gravity, trying to pull everything inward, versus the explosive pressure generated by nuclear fusion in their core, pushing outward. This balance keeps the star stable. But eventually, the star runs out of lighter elements like hydrogen and helium to fuse. It starts fusing heavier and heavier elements, carbon, neon, oxygen, silicon, each stage burning faster and hotter than the last. This continues until the core is mostly iron. Iron is fusion's dead end. Fusing iron atoms doesn't release energy, it absorbs it. Suddenly, the outward pressure from fusion vanishes. Gravity wins. Instantly and catastrophically. In a fraction of a second, the core collapses. Imagine the entire mass of our sun, or much more, squeezed down from a sphere hundreds of thousands of miles wide into a city-sized ball, maybe just 20 kilometers, 12 miles, across. The force is unimaginable. It's so powerful that it overcomes the fundamental forces that usually keep atoms apart. Under normal circumstances, atoms are mostly empty space. A tiny, dense nucleus, made of protons and neutrons, sits in the center, surrounded by a vast cloud of whizzing electrons. The electrons whizzing around keep atoms from overlapping too much. It's like they have personal space bubbles. But in the core collapse of a massive star, gravity becomes so overwhelmingly strong that it crushes even this atomic structure. The force is so immense that it smashes the electrons right into the protons in the nuclei. When an electron, negative charge, and a proton, positive charge, are forced together, they cancel each other out and transform into a neutron, neutral charge, and a neutrino. This process, called neutronization, happens almost instantly throughout the collapsing core. The result? An entire star's core transformed almost entirely into a sea of neutrons, packed together with almost no space between them. This is a neutron star. It's not made of atoms anymore. It's essentially one giant atomic nucleus, but made only of neutrons, squeezed together tighter than anything else in the known universe. This is where the density comes from. Density is simply mass divided by volume, how much stuff is crammed into a given space. Neutron stars win the cosmic density contest hands down because they pack an insane amount of mass, more than our sun, into a volume so small it's laughable. Think about it. The sun has a diameter of about 1.4 million kilometers. A typical neutron star has a diameter of about 20 kilometers. That means you could line up 70,000 neutron stars side by side to span the sun's diameter. To match the sun's volume, you'd need hundreds of millions of neutron stars. But here's the kicker. A neutron star contains at least 1.4 times the mass of our sun, and often up to about 2 times or a bit more. So, you're taking all that mass, all the material that once filled a colossal sphere hundreds of thousands of times wider than Earth, and crushing it down into a ball you could drive across in an hour. It's like taking Mount Everest and squeezing it down to fit inside a single sugar cube. That's the level of compression we're talking about. The density becomes astronomical, roughly 1 billion tons per cubic centimeter. That's why your teaspoon, which holds a few cubic centimeters, would weigh 1 billion tons. A single sugar cube-sized chunk of neutron star material would outweigh every ship in the world's combined navies. A marble-sized piece would rival the mass of a large mountain range. Its matter stripped down to its absolute bare essentials, compressed beyond anything we can replicate on Earth. So, how does matter even behave under such insane pressure? What holds it up against collapsing further into a black hole? The answer lies in a fundamental quantum mechanical principle called the Pauli exclusion principle. In simple terms, this principle states that certain types of particles, like neutrons, cannot occupy the exact same quantum state. They refuse to be squeezed into the same space doing the exact same thing. Think of it like trying to pack people into an elevator. At some point, you just can't fit any more people in without them violating each other's personal space. They push back. Neutrons are the ultimate claustrophobic particles. When gravity tries to crush them even closer together in the neutron star, the Pauli exclusion principle kicks in. The neutrons resist being forced into identical states. This resistance generates an immense outward pressure known as neutron degeneracy pressure. It's this quantum mechanical "I need my space" force that counteracts gravity and prevents the neutron star from collapsing further. It's the absolute limit of how densely matter can be packed without becoming a black hole. If the collapsing core had been just a little bit heavier, above roughly 2 to 3 solar masses, even neutron degeneracy pressure wouldn't be enough, and gravity would win completely, forming a black hole. But for neutron stars, this quantum standoff holds. But neutron stars aren't just inert, ultra-dense balls. They're cosmic powerhouses, spinning insanely fast and boasting magnetic fields that defy belief. Remember that collapsing star core? Like an ice skater pulling in their arms to spin faster, the core spins up dramatically as it shrinks. A star that might have rotated once every few weeks can collapse into a neutron star spinning hundreds of times per second. That's surface speeds approaching a significant fraction of the speed of light. Many neutron stars also emit beams of intense radiation, radio waves, X-rays, gamma rays, from their magnetic poles. If these beams sweep across Earth as the star rotates, we detect them as incredibly regular pulses, like a cosmic lighthouse. We call these pulsating neutron stars pulsars. The Crab Nebula pulsar, the remnant of a supernova observed in 1054 AD, spins about 30 times per second. Millisecond pulsars can spin over 700 times per second. These precise cosmic clocks are some of the most accurate timekeepers in the universe, helping scientists test theories of gravity and measure cosmic distances. Then there's the magnetic field. Normal stellar magnetic fields are powerful. Earth's protects us from solar wind. Neutron stars take this to ludicrous extremes. During the collapse, the original star's magnetic field gets squeezed and amplified along with everything else. The result? Magnetic fields a quadrillion, 1,000 trillion, times stronger than Earth's. We're talking 10 to the power of 12 to 10 to the power of 15 Gauss. An MRI machine uses magnets around 10,000 to 70,000 Gauss. A neutron star's field is strong enough to rip molecules apart from thousands of kilometers away. It warps the very structure of atoms and influences the behavior of the superdense matter itself. Some neutron stars, called magnetars, have the strongest magnetic fields known in the universe. Their fields are so powerful they can crack the neutron star's crust, triggering massive star quakes that release colossal bursts of gamma rays and X-rays, some of the brightest flashes in the universe since the Big Bang. What would happen if you could actually bring a spoonful of neutron star material to Earth, which is utterly impossible? The moment it left the crushing gravitational field and immense pressure of the neutron star, the neutron degeneracy pressure holding it together would vanish. The neutrons, no longer squeezed beyond endurance, would immediately start to expand. They would decay back into protons and electrons, reversing the neutronization process, releasing a colossal amount of energy in the form of radiation and particle explosions. The release would be catastrophic, equivalent to a massive thermonuclear bomb, vaporizing everything nearby. The exotic state of matter simply cannot exist outside its unique, ultra-extreme environment. It's a substance forever bound to the unimaginable conditions that created it. Discovering and studying neutron stars is a triumph of human ingenuity. We can't see them directly with optical telescopes, though some hot ones are visible in X-rays. Their discovery came indirectly through pulsars. In 1967, Jocelyn Bell Burnell, a graduate student, detected incredibly regular radio pulses coming from deep space. Initially dubbed LGM, one little green men 1, they were soon understood to be the lighthouse beams of a rapidly spinning neutron star, the first pulsar. Since then, telescopes across the electromagnetic spectrum, radio, X-ray, gamma ray, have found thousands. The Hubble Space Telescope has even imaged a few relatively nearby ones. Gravitational wave detectors like LIGO and Virgo are now listening for the ripples in space-time caused by neutron stars colliding, events that forge heavy elements like gold and platinum. Each observation peels back another layer of the mystery surrounding these extreme objects. The existence of neutron stars, and that insane teaspoon fact, does more than just boggle the mind. It teaches us fundamental lessons about the universe. It shows us the incredible power of gravity when unleashed. It reveals the counterintuitive power of quantum mechanics acting on cosmic scales. It demonstrates the dramatic transformations matter undergoes under extremes we can barely fathom. That spoonful represents the ultimate victory of physics over structure, pushing matter to a state where atoms cease to exist, and only the raw components of nuclei remain. It's a direct consequence of Einstein's theories of relativity meeting head-on with the bizarre rules of the quantum world. Neutron stars are cosmic laboratories, testing the laws of physics under conditions we can never recreate on Earth. They remind us that the universe is capable of phenomena far stranger than fiction, forged in the hearts of dying stars. So, the next time you stir your coffee or spoon some sugar, take a second to imagine the inconceivable weight and cosmic history contained in a neutron star teaspoon. It's a humbling dose of perspective, a reminder of the sheer scale and power at play in the cosmos, and a testament to the incredible journey matter takes, from the diffuse clouds of stellar nurseries to the unimaginably dense relics of stellar demise. It's the universe showing us just how far the rules can bend, and how truly spectacular the results can be. Thanks for pondering the extreme with me today. Stay curious, stay healthy, and keep looking up in wonder.